Hi, this is Dr. David Brenham. Today we're doing a video on ordinary least squares regression. It's a post facto design model that you can use with data from out in the field. And so let me get started with a PowerPoint presentation that I will share my screen to get to. Okay, share. We see the start of an ordinary least squares regression equation. That's the first thing we need to talk about when we're talking about ordinary least squares is the equation. Because when you run it on the computer, you'll get this output. But this output actually works inside of an equation, and that equation is in your reading. And you can see that equation up here. It's a y hat. You see a little triangle on top of the y. That means y hat. And y hat means it's your prediction of y, or your prediction of the dependent variable. So your prediction of the dependent variable in a regression model equals a plus bx1 plus bx2 all the way out, depending on how many variables you have. Okay, you can have one variable in a regression, or you can have 10, or you can have 20. Once you get to 20, things start to get problematic. But you can have a lot of different variables in a regression. And this is important because it allows you to do things like control for outside factors and things like that. And it's what makes regression such a valuable tool. So in the equation, y hat stands for the predicted value of the dependent variable. So that's what we're going to try to do, is predict the value of a dependent variable. A stands for the constant. It's also known as the base. If all of the values of your independent variables are 0, then A will equal the predicted value of Y. Okay, that means if all your variables are set at 0, where all the values are at 0, which means 0 times 0 would be, or 0 times whatever the coefficient is would be 0, then A is your predicted value for Y hat, or the predicted value of your dependent variable. Okay, B stands for the independent variables in a regression. So regression models can have multiple independent variables, as can be seen in this equation. It can have one independent variable, it can have several. But B stands for the dependent variable. X next to the B, or the independent variable, stands for the regression coefficient. This is the value the independent variable is multiplied by to find its impact on Y. Okay, so when you have a regression, you'll need to know which each one of these stands for, because that way you'll be able to fill in the prediction equation for your variables. This could be very important to know for the test. You need to know all of these for the test, and you need to know all of these for the assignment. Any assignment that you have on regression, and actually using the regression equation to make predictions, any of that, you will need to know all of these. Now, the regression table basically is set up like this, where the dependent variable in this model is years of education. It's just a basic dependent variable, and what we're trying to do is predict the years of education each individual in a sample will have. And we have two independent variables to find out to help predict the years of education. One is a gender variable for man, and I put man there because you want to specify what the gender is, because in each of these categorical variables, like gender, a value of 1 is set for the man. Excuse me. A value of 1 is set for the man if it's labeled man. If it's for a woman, then it will be the value of 1 is set for the woman. But in this case, it's man. So if you're not a man, you're 0. And if you are a man, you're 1. So that's how it's set in the equation. The other one is a categorical variable that simply asks, do your parents have a college degree? That way, if there's a college degree in the family, set at 1. If your parents don't have a college degree, it's set at 0. Excuse me. Last is the constant. We saw what the constant was in the regression equation. Y hat equals A plus bx1. So y hat, which is the dependent variable, in this case, years of education, equals A, which is the constant, which will be 13, okay, plus bx1 plus bx2. So bx1 would be man would be B. The coefficient would be set would be there at -1. bx2 is B. Parents have a college degree. The coefficient is 2.0. That's the x2, and here we can see it. So it's a simple equation. If all your independent variables are set at 0, what you'll end up having is you'll have man, you would have a woman because they're not a man, they'll be set at 0. Your parents don't have a college degree, so that will be set at 0. The constant would be 13. So your prediction would be for a woman with parents with no college degree, the prediction would be 13 years of education. If you were a man and your parents didn't have a college degree, it would be y hat equals -1, excuse me, y hat equals 13 -1 or plus -1, which is man. And if you don't have a college degree, it would be 0. So if you're a man and your parents don't have a college degree, your expected level of education is 12, which is 13 plus -1, which equals 12. Okay, so the regression equations you use on the last page, you can use your coefficients and your standard error and t-scores that we see up here in this regression table. We can use that. We use that to actually make a prediction for y for your variables. Okay. The other thing that this table has, as I said, is the standard error. Your tables should have a standard error, and the tables have a t-score. That's nice. And then it has a star on the t-score. You'll see the star there. Those stars mean it's significant at the 0.05 level for a two-tailed test. You see that at the bottom. That's what those stars stand for. N stands for the number in your sample. So this is a regression with 300 people in it. And the adjusted R-square is 0.2, which means that 20% of the variance besides the mean is explained by these two variables in the model. So we have models predicting years of education. Okay, we see some conclusion of the model. 1, categorical independent variables in regressions are coded 1 if the person is in the category and 0 if the person is not. So this is something I said on the last page, but I just want to clarify here that for the variable man, if you're a man, you're coded as 1. If you're not a man, you're coded as 0. The same with those categorical independent variables, parents have a college degree. If your parents have a college degree, coded 1, 0 if they do not. So that's how you categorize these variables, and that's how they're coded. Therefore, each man in the sample is coded 1 for the variable man, and each woman is coded 0 for the variable man. And these are the X values for that equation. Therefore, each person with parents who have a college degree are coded 1 for parents who have a college degree, and each person who does not have a parent with a college degree is coded 0. Those codes are there. I know I'm repeating myself from the last slide, but these notes on the right-hand side will let you read these notes and be able to replay this and see what we're doing here with this regression equation. All persons in the sample begin their prediction of years attending school with the value of 13. That's the constant. So after the 13, the values of the other independent variables are applied to predict what the peers they want to, excuse me. After 13, I have a typo there. After the 13 values of the other independent variables, after the 13, the values of the other independent variables are applied to predict the years, not the peers, the years that they went to school. So, as I did before, you start out with 13, then you ask, is this a man or not? If it is, you subtract 1 for 12. Then you ask, does this man have parents with a college degree? If they do, you add 2.0, and then you would predict that the man would have 14 years of education. That would be the prediction. Women with parents who have college degrees are predicted to have 15 years of education. We can see from the equation, y hat equals 13, which is A, which equals -1 times 0 for being not a man, so which equals 0, plus 2 times 1, because the parents do have a college degree. So the prediction is y hat equals 13 plus 0 plus 2, which equals 15. You would predict that this woman would have 15 years of education. That's what the regression model does, is it predicts that it has that prediction equation. Men with parents who do not have college degrees are predicted to have 12 years of education. As we said before, y hat equals 13, which also equals -1 times 1, which means they're a man, plus 2 times 0, because parents do not have a college degree. So it would be y hat equals 13 plus -1 plus 0, which equals 12. So the prediction for a man with parents without a college degree is for that man to have 12 years of education. Other conclusions. One, this table tells us that the number in the sample was 300. That's a nice large sample. So the number was 300. The prediction model says that men are likely to go to school 1 year less than women because they have that -1 coefficient. A hypothesis that men will have less college years than women will fail to reject the null hypothesis because the t-score is not lower than -1.65. So this is a negative directional hypothesis. Men will have less years of college education. If we run it in this regression, yes, we get that negative coefficient. And for a prediction, you always go ahead and use that negative coefficient. But if they're asking, are men significantly less likely than women to have, are significantly less in years of education than women, excuse me, that hypothesis would fail to reject the null hypothesis because the -1.5 t-score is not lower than the -1.65 required. So if that's the case, remember that in the regression, it gives you basically a mean prediction. And what happens here is men overall, all things equal, are in the model are expected to go have 1 less year of education than women. But that 1 year is not statistically significant. So on a hypothesis test, that would fail to reject the null hypothesis. Children of parents with college degrees are predicted to go to school 2 more years than those who do not have parents with college degrees. That is clear there. The coefficient is 2. Okay. The hypothesis that children of parents with college degrees will go more years to school than children of parents without college degrees will reject the null hypothesis because the t-score is higher than 1.65. This is also a directional test. It's basically saying my hypothesis is that people who have parents who have college degrees will go to school more years than people who don't. The t-score on this is 3.0. On this directional hypothesis, that 3.0 far surpasses the 1.65 required to reject the null hypothesis. So in this case, we would reject the null hypothesis and say that the evidence does suggest statistically that people who have parents with a college degree will go to school more years than people who have parents without college degrees. The evidence is significant that the children with parents with college degrees will go to more years of school. Another conclusion, the t-score for the constant, see the constant has a t-score there of 10. It's a pretty large t-score. So it's significant, and we see that it's significant. What does that mean? The t-score for the constant only looks to see if the constant is different than 0. So our constant is clearly different than 0. We start at 13 and then work from there. 13 is a long way from 0, hence the huge t-score of 10. And that makes sense. So while the t-score is significant in this case, and the t-score is very large, it really doesn't have much meaning. We would not expect a model predicting years of education to start at 0. The model starts basically where it would be if all the coefficients were set at 0, which is 13. So yes, it is significantly different than 0, but who cares? That's basically what happens in regression models. So when you see huge t-scores and statistical significance for the constant, in regression, don't even worry about it. It's just where you start, your starting point is. And it's asking, is my starting point 0? The adjusted R square of 0.20 means that the model predicts 20% of the variance in the dependent variable, that the mean does not. It starts at the mean. So we know that the best predictor of, if we have no information at all, the best predictor of what a person will be, for instance, in years of education, is to look at the mean. If we know the mean and say it's 13, we know the mean is 13. The best prediction, if you know nothing about a person and they ask you, how many years do you think they went to school, is the mean, it's 13. But when you know these variables, these independent variables, you know gender, you know whether the parents have a college degree, your prediction gets better. In this case, in this model, those two variables allow our prediction to get 20% better. So our prediction error is 20% better than it would be if we didn't have the model at all. Another conclusion, it could be that women who have parents with college degrees are more impacted by that than men. You see, the previous model that we had, I'm gonna go up, page up. See the previous model? This previous model, it assumes linearity. It assumes that your parents having a college degree will have the same value for a man as it does for a woman. It assumes linearity between the independent variables. That may not be the case, and it's often not the case. So in regression, we have the ability to change that and make it where we can look and not assume that these are linear. And we would do this by basically categorizing the variables and putting those variables together so that we can look at the effects on men and women of their parents having college degrees. It could be that women who have parents with college degrees are much more impacted than that by men. One way to test this nonlinearity would be to combine the variables. And to do this, you put 3 variables in the model and leave out one to prevent perfect multicollinearity. This is something you'll probably see later in your assignments. For instance, you can have the variable men with parents with college degree. That'd be 1 if that was in the category and 0 if they weren't. Second variable, men with parents without college degrees. That'd be 1 if you're in that category, 0 if you're not. The next one would be women with parents with college degrees. It'd be 1 if the person was in that category and 0 if not. And then the fourth variable, which would be women without parents with college degree, would be left out of the model. Now, why would we leave this out of the model? Because if we put it in the model, we would have a perfect prediction with the variables and we wouldn't be able to see the actual impact of the variables. What we do is we leave this categorical variable out, women without parents with college degrees. When you do this and you set up the model like we have here, notice there's no coefficient or standard error t-score yet. We haven't run the analysis, we've just changed the variables. And so what we do is we leave women without parents with college degrees out. And we would predict that value by looking at the constant, which would be the base. So what we're saying is women without parents with college degrees are the base, okay? And since they're the base, then we can compare the other 3 variables to them to see if having parents with a college degree affects men and women differently. So if we go to the next page with the coefficients, standard errors, and t-scores in there, we do see that in this particular set of data, that women are much more affected if their parents have a college degree than men are. We can see the coefficients for men without parents, with parents with a college degree, and men without parents that have a college degree are both 0. To men, in this data, it doesn't matter whether their parents have college degrees or not. They're predicted to be 0 on the coefficient. They're the same whether they have college degree, their parents have college degrees or not. That would mean that their predicted value would be the constant, 12.5 plus 0. So you would expect all men, no matter what, to have 12.5 years of education. We would also expect women without parents with college degrees to also have 12.5 years of education because they're the base. They're the variable that's left out. The one variable left in that is significant, look, it has a t-score of 4.5 here. It has a coefficient of 4, is women with parents with college degrees. So when you compare women with parents with college degrees to women who do not have parents with college degrees, you see a massive difference in expected years of education, 4 years in fact. So we would expect women with parents with a college degree to actually go to school for 16.5 years, while everybody else in the entire model would go for 12.5 years. See the difference, even though the data is the same, see the difference when you recategorize the variables to take out that assumption of linearity, that assumption that parents with a college degree have the same impact on men as they do on women. Take that assumption out and recategorize, the linearity goes away. And we can see, oh, all of a sudden, women are much more impacted by their parents than men are. That men aren't impacted by their parents' education at all. So in this particular model, that linearity assumption is proven wrong. This is something you probably will see later, where in experimental design, where we assume that everybody is impacted the same by every variable. And if we were doing experimental design, we would have parents with college degrees compared to parents without college degrees, regardless of gender, and we would find that effect was much more weak. But when we do it like this, we find, oh, all of a sudden, look, it's women who are affected by their parents, not men. So this is a great way for regression to allow you to throw away that assumption of linearity and look and see what's going on. So know this for your test and know this for your assignment going forward. I want to thank you for taking the time to look at this video. I'm hopeful that it will help you. Remember, it's supplementary. Your test answers officially come from your reading, but I don't believe there are any contradictions here. And I also believe this video will help you in doing your tests and your assignment. Thank you for spending this time. Have a great day.